screen with us and to start his presentation.
Just a second. Okay. You can see my screen, right?
Yes, we see it.
Okay, thank you. Thank you. Okay, so I apologize. First of all, I apologize. I don't have a camera, so yeah. First of all, I want to thank the organizers for the kind invitation, making me a part of this conference in honor of late Professor Bartolucci. So most of my results that I will present today are joint work with Hans Feintiger and Stevan Filipovic. But on a couple of occasions, I have to recall some older results that were obtained with Pavel Dymowski and Jason Windows as well. So to start, modulation spaces are a cornerstone in time frequency analysis, but the classical ones that we already know are usually defined in terms of the weighted mixed norm Lebesgue spaces LPQ. So we were particularly interested here in modulation spaces that are obtained from tensor products of two different LP spaces. However, for this reason, I will first have to make a slight detour and introduce a generalization of modulation spaces so these new ones will fit in the theory. So to start, let me just first fix the notations. So I will denote by T sub x and M sub xi the translation and modulation operators. They are standard ones. For a fixed window, non-identically zero function in the Schwarz space, the short-time Fourier transform of a tempered distribution is I will denote by Vg of f, and its adjoint I will denote by Vg star of the function phi in this concrete example here. And I will just stress one identity is that the composition of the adjoint of the short-time Fourier transform with the short-time Fourier transform is always the identity times a scale times a scalar, and this is just the inner product of G with itself. Okay, so now to start, before I introduce the generalizations of the modulation spaces, I first have to recall the notion of a translation-modulation invariant Banach space of distributions. So these are Banach spaces E, which satisfy these three assumptions. I will just emphasize the third one, which basically states that when you take the operator norm of the translation, it is polynomially bounded with respect to the parameter x, and also the operator norm of the modulation. We ask the operator norm of the modulation to be polynomially bounded with respect to the parameter psi here. And one can define now two weight functions for the space E. Omega sub E of x will just denote the operator norm of the translation, and nu sub E of xi will be the operator norm of the modulation. And these two functions now are obviously submultiplicative, and the third condition actually imposes on them polynomial bounds. I will always call these functions the weight functions for the space A. And of course, if E is a translation modulation invariant, then the Fourier side of E, the Fourier image of E, is also translation modulation invariant. And this is simply because of the fact that the Fourier transform changes the translation into modulation and vice versa. Just a few examples before I continue. So if eta is a polynomially bounded weight, then the weight at LP spaces, weighted by the weight eta, are translation modulation invariant, of course, for P between 1 and infinity, but excluding infinity, because if you take L infinity, the first axiom fails, because the space S is included in L infinity, but it's not dense. That's why we exclude the case P infinity. Next, but the space C eta, it is the space of continuous functions, such that when you multiply them with the weight, they vanish at infinity, is a translation-modulation invariant. And of course, because of the both, their Fourier sites, the Fourier images, are also translation-modulation invariant. So now let G be a fixed window in the Schwarz class, in the Schwarz space, and let X be any translation-modulation invariant space on R2D. Then we define the modulation space associated to X in the following way. So it is the set of all tempered distributions, such that when you take their short-time Fourier transform, you end up in the space X. And by the mere definition, it should be obvious that if you take X to be the mixed norm LPQ space, then you end up with the ordinary modulation space. What is important here is that MX is, of course, always a Banach space, and it does not depend on the window. And in fact, it satisfies most of the properties that you already know for the classical modulation spaces. For us, it will be particularly interesting when X, so the model space for which you generate the modulation space, is not a mixed norm LPQ, but it's a tensor product of two LP spaces. That will be a particularly interesting case. And because of this, before I continue, I have to just briefly recall the notion of the two main topologies, two main norms on the tensor product of two Banach spaces that one can introduce. And first, first I will recall the pi top norm, or the projective norm, and it's defined as the infimum of these quantities, where the infimum is taken over all possible representations of U as a sum of simple tensors. And one can prove that this is indeed a norm. And when you complete the tensor product with respect to this norm, you get a Banach space, of course, and I will call this Banach space the completed pi product. And for the completed pi product, the following thing will be particularly important. And this is the Grothendieck representation of the elements of the completed pi product. It basically states that every element of this Banach space can be represented as an absolutely convergent series, such that the xj's and the yj's are bounded by a single constant in x and y respectively, and the lambda j's are complex numbers, such that the series of lambda j is absolutely summable, absolutely convergent. So this is the pi norm. And now for the epsilon norm, for this I have to recall that the tensor product can always be viewed as a subspace of the space of bounded bilinear forms on the duals x prime and y prime. And this, the way you associate to each tensor bilinear form is in the following way. So you take an arbitrary tensor, and the induced bilinear form is given by the sum. And one can prove that this is indeed a well-defined continuous bilinear form. And this association is indeed injective. And then you define the epsilon norm on the tensor product as simply as the norm which is induced on the tensor product from the space of bilinear forms, continuous bilinear forms on x, y, x prime and y prime. Of course, then when you complete this space, you get a Banach space, and I will call this Banach space the completed epsilon product. Just a few remarks here. The pi norm is always stronger than epsilon norm, and if the spaces x and y satisfy a very particular assumption, then the completed pi product is always a subspace, of course, continuously included into the completed epsilon product. But I won't go into the details what is this assumption, because this is always satisfied in the case of translation-modulation invariant spaces. Just to recall, in general, that the completed pi product doesn't have to be a subspace of the completed epsilon product, although the norm is always stronger. Okay.
Bojan? Bojan, please. Okay, it's okay. Sorry, we lost your presentation for a moment, but now it's on again.
Okay.
Sorry, you can continue.
Okay, sorry. I guess, okay. So the first important result is that if E and F are both two translation modulation invariant spaces on RD, then their completed pi product and their completed epsilon product are again translation modulation invariant, but now on R2D, of course. And this is interesting now for us because if you take for E and F to be two LP spaces, you can take their completed pi product or epsilon product, and you get a translation modulation invariant space on R2D, and you can generate the modulation space which is associated to it. And our goal in this talk is to identify how this space looks like, in a sense, to express it in terms of already known spaces. For this reason, I have to recall one very interesting thing, is that, for example, if P1 and P2 are between 1 and 2, and P1 is less than P2, then this modulation space is always included into the classical L1. And as a consequence of this, you can immediately, it's not directly, but one can deduce that this modulation space, for example, is always different than the classical modulation spaces constructed out of LP. Okay, so now the question is, what is the modulation space associated to LP tensor, completed tensor product with LP2? And for this reason, I will now need the Grothendieck representation that I mentioned before. So take any F in the modulation space, and this means that the short time, by the definition, the short time Fourier transform of F has to lie into the completed pi product of the LP1 and LP2, which by the Grothendieck representation just means that you can represent it as an infinite series of this form. And then you take the adjoint of the short time Fourier transform, and this gives you a way how your F has to look like. So it has to be a sum, absolutely convergent sum of this form. And now let's stop and think about it for a second. Recall that from the Grothendieck representation that the phi j and the psi j have to be bounded by a single constant. And this, because G is in the Schwarz class, this means that when you take the convolution of G with phi j, you always end up with a C infinity function, but not just that it's C infinity, but it's uniformly bounded in C infinity, because the phi j's are bounded in LP1. So this means that no matter how F looks like, its local behavior won't be affected by no means by the local behavior of phi j. So the first component, the LP1 here, won't be affect in any kind of way the local behavior of F, because this in the sum this always ends up as a bunch of smooth functions which are uniformly bounded. So the local behavior only will depend on the second component, on the LP2, and this is somehow reflected here as the local behavior of the inverse Fourier transform of the psi j's. However, the global behavior will depend, of course, on both the P1 and P2, because the sum has to be absolutely convergent simply because of the Grothendieck theorem. So when we realize this, we quickly understand that the correct problem to look at is not the tensor product of two LP spaces, but in fact the tensor product of two amalgam spaces. And for those of you who are not familiar with amalgam spaces, I will introduce them in a minute, but by their mere definition, they keep track both of the local behavior and the global behavior of the function, which is exactly the thing that appears here in the sum. And then we will deduce from this general result about amalgam spaces, we'll deduce the result for the tensor product of two LPs. Okay, so for this reason, let me recall the definition of amalgam spaces. So this can be done in a far more general setting, but for us, it's the only thing important is the case when E is a translation modulation invariant. So let E be such a space and define E log as the space of all temporal distributions, such that when you multiply them by a compactly supported smooth function, you end up in the space E. So these are, in a sense, all the temporal distributions that locally look like E functions. and take the very specific kind of partition of unity. And then one defines the amalgam space with local component E and global component LP. Here, LP stands for the ordinary sequence space LP, to be the space of all elements of E log, such that when you multiply them by the partition of unity and take the E norm of that, you end up with a sequence with an element in the sequence space LP. And that's how you produce the norm on the space. Similarly, one can introduce the amalgam space with global component C0, where C0 stands for the sequence space of all sequences which vanish at infinity. And you can define it in a completely analogous way. And let me just briefly state that the definition of the spaces does not depend on a partition of unity. So in a sense, any partition of unity which is good enough in a certain sense will produce the same kind of same space. And for us, it is important that if E is a translation modulation invariant, then all of these amalgam spaces will be translation modulation invariant. And furthermore, they satisfy this chain of inclusions always. And the space E always lies somewhere in between. This is for us good because the amalgam spaces provide in a certain way a good bookkeeping device, because they categorize the elements which are in E log by their growth conditions in a certain way. And the space E is always, of course, somewhere in between. Just quickly to recall that if you take E to be an LP, then you can exactly identify where the space E is, because it's exactly at the point which has a global component P. Because if you have a local behavior like LP and global behavior like LP, you end up with an LP. Okay, so now my theorem, our theorem, is the following. So we take E and F to be any translation modulation invariant, and we impose only one condition on F, and that is that the translation group is bounded. So just recall that omega F stands for the operator norms of the translation group. So if it is bounded, then all of these modulation spaces associated to these tensor products are the same. And not that they're just the same, but they're exactly equal to the amalgam space with local component E and global component L1. And this exactly reflects the thing that I mentioned before, that the space F, which appears here, has no effect on the modulation space at the very end, because you see it practically disappears. And this is the fact that I mentioned before, that the local behavior is not important. The global behavior is important, and it's reflected in the second component in LP1 here. And once we have this theorem, now we can deduce a lot of things from it. And because I do not have much time left, I'll just state a bunch of consequences of this thing. So first of all, the first thing is the original problem. So the tensor product of LP1 and LP2, when P1 and P2 are between 1 and 2, is always the amalgam space of the Fourier site of LP2 with global component L1. And we also have a bunch of other immediate consequences of this. Let me stress one more thing. The third one, again, the same thing, the space F completely disappears, because no matter what is F, you will always end up with an amalgam space of type EL1. And besides the P product, once we had this, we can more or less generalize it also to the epsilon product, where the things are not so easy, but we managed to do it. And we have an analog variant for the epsilon product. Notice here that the space you end up with is C0. It's not L1, but it's C0, and this somehow reflects the thing that the pi norm goes well with absolute summability, and you always, because of that, you always end up here with L1 norms, and the epsilon norm always goes well with L infinity types of norms, with supremum norms, and that's why you end up with C0 space. Okay.
Okay, thank you, Bojan. Thank you very much. don't know whether there are any questions here, because as I was informed, there are no questions on our chat. I remind you that if you want to pose a question to the speaker, then please send your question to the chat, but to all participants. That's the way that we can see it. And maybe someone here in the room. No questions.
Since we discussed, this is very, very new, so we discuss every day, finding evenly, so somehow no question from my side.
Okay, so if there are no questions, then thanks again, Bojan. Thank you.
Thank you.
So, there is a question. So.
Are they resolved ultra-distributions for ultra-distribution analogs?
Yes, I can see the question. Yes, okay, so first of all, okay, can I share my screen again, please?
Of course, just a second.
Because it will be easier to explain it on the presentation.
I will put you just...
Okay, that doesn't matter. Okay, so,
no, you are on. You can share it.
I can share it, okay. Okay, so the one thing that you can, it's probably it's very plausible to extend it to ultra distributions, but the trick that we really use here is this partition of unity, which is of compactly supported functions in order to define the amalgam spaces. So if one can define amalgam spaces, of course now for ultra distributions, one has to take functions which do not have compact support, because I'm assuming that Jason's question is concerning quasi-analytic classes. Then most of the theory will probably work, and this will be particularly interesting for Jason, that both in the epsilon product and the pi product, one of the key ingredients was a Dixmeyer-Maliavan type of result, because we had to split the window in the convolution sense. So, but because we already have these kinds of things in our paper with Andreas, so probably that part will work well. The problem here is the fact that you have to define the amalgam type spaces for quasi-analytical distributions.
Okay, topology it is okay, but for epsilon it is, because this theorem is somehow problem for the epsilon product. Is it?
But
because we have this separation of a function from B into function in S and in B.
Yes, I understand what you mean, but that's why I said that if one can define the amalgam spaces for quasi-analytic classes, so without functions with compact support, then probably in the same way you can do for the epsilon product without using functions with compact support that we did in the proof. Yeah, because if it works for the amalgam spaces, they will probably work in the proof in the same way. And the key component here is the splitting of the functions, which we already have in the paper with Jason and Andreas. So my answer is probably yes, if you can construct the amalgam spaces.
Okay, thank you, Bojan. So,
I will stop sharing.
We are just waiting for Professor Feitinger. Can you read, Bojan, the question for Professor Feitinger?
Yes, now I can read. Wait,
let me see.
Jason is from Feitinger.
You say no problem to extend the formula.
Yes.
No problem to extend the formulas, for example, using word collection from
Yes. Okay, then Hans already answered it. Yes, Hans already answered it.
Okay, so it was just a comment or something, yeah. Okay, thank you very much, Bojan, again.
Thank you. Thank you.
So we can now proceed with our next speaker. This is Giorgia Bellomonte, and the title of her talk is Frames and Weak Frames for Unbounded Operators. So, Giorgia, please, you can share your screen and start the presentation.
Okay, can you see it?
Yes, we can see it.
Yeah,
excellent.
Okay, so I thank organizers for this opportunity. I'm Giorgia Bellomonte. I'm from Palermo, and I'm going to talk about frames for unbounded operators. If we take my work originates from a paper by Gavruta in 2012, and she considered a bounded operator in Hilbert space H and a sequence of vectors in H, and she said that it was the sequence was an atomic system for K if it was a Bessel sequence of K of H. Sorry, and if there exists a positive constant C such that for every F in the Hilbert space there exists a sequence in L2 A sub F such that these two conditions are hold true. So she can reconstruct the whole range of a bounded operator by means of vectors G sub n. She proved a characterization for the atomic system for a bounded operator because she proved that if we have an atomic system for a bounded operator K, then it is equivalent to having what she called a K-frame for H. There exist two positive constants, alpha and beta, such that this double inequality holds true for every F in H, and both are condition 1 and condition 2 are both equivalent to the third one. There exists a Bessel sequence such that the range of K can be reconstructed this way. What is interesting about this possibility is that the elements in the reconstruction of the range of K do not necessarily belong to the range of K. So me and a colleague of mine, Rosario Corso, tried to we extended in a discrete framework those two notions of atomic system for a bounded operator and atomic and K-frame to unbounded operators, and then I made the same work in a continuous framework. So if we have a measurable space and we have a Hilbert space H and a closable densely defined operator A, and if we have psi, a Bessel family for, in H, we want to decompose the range of this operator, this closable densely defined operator, weakly, this way, I mean. But if we have a bounded if we have an unbounded operator A, this function in L2 can't depend continuously on F, differently to what occurs when A is bounded, and so we need somewhat which takes on the boundedness of A. We have to overcome the boundedness of A in some way. We thought to two approaches. One involves, sorry, I don't know what happened. One approach involves a continuous Bessel family and the coefficient function AF. It depends continuously on F only in the graph topology of A. The other approach involves a non-Bessel family, but the coefficient function AF depends continuously on F and in the domain of the operator A. Today we will see this latter approach. recall that in 1993, and then independently in 1994, Ali Antoine Gazeau and Kaiser defined a continuous frame for a Hilbert space. A continuous frame for a Hilbert space is a family of vectors for which this is a measurable function on X for every f in H, and there exists two positive constants alpha and beta such that this double inequality holds true for every f in H. In particular, the family psi is called a Bessel family if at least the upper condition in two holds, and if alpha and beta are equals to 1, then the family is called a continuous Parseval frame. Sorry. So what is a continuous with K frame? If we have a densely defined operator on H, a continuous with K frame for H is a family psi such that this map is a measurable function on H for all f in the domain of the adjoint of A, and this condition is fulfilled for every f in the domain of the adjoint of A. Of course, if X is the set of natural numbers and mu is a counting measure, a continuous with K frame reduces to a discrete with K frame in the sense of the work with Rosario Corso. And if A is a bounded operator, a continuous with K frame is an AG frame for H in the sense of Alizadeh, Rahimi, Osgo A, and Ramani. But in a discrete framework, if A is a bounded operator, this concept reduces to the notion of Gavruta that originated our exploration, our investigations. If we have a densely defined operator on H and a continuous frame for H psi, A psi is a continuous with K frame for H, and it is simple to see, because if we take this adjoint to the second entry in the inner product, it is very simple to say to see that A psi is a continuous with K frame for H. An example is here. If we have an example of a continuous with K frame, I mean, if we have the real line and we take as a measure the Lebesgue measure on the real line, and if we take as a Hilbert space the space L2 on the open interval 0, 1, and I is the identity of this space, and we take A as this operator with this domain, this function defined like this is a continuous with K frame for L2. In fact, it is the image through A of this function that is a Parseval function. So as I said before, it is a continuous. You know what is what's the definition of the synthesis operator of a family in Hilbert space? It is an operator defined like this. It is not densely defined in general, hence the adjoint is not well defined in general. There are examples in which D is densely defined, because if we take the mu as the Lebesgue measure on X, then the domain of D is dense because it contains the space of continuous functions with the compact support contained in X. You know what is the analysis operator is an operator defined, as you can see here, And you know that in it is a literature in the discrete case, if we have a sequence of elements in H, then C is equal to the adjoint of D. If C is densely defined, then D is extended by the adjoint of C. D is closed if and only if C is densely defined and D is equal to the adjoint of C, and C is closed. However, not each of these properties holds true in the continuous case. We can, in general, recover at least two of them. In fact, if X is a sigma finite measure space, then C is closed, and I proved it. It is a similar result to a result of Antoine Balach in 2011. However, they supposed that the family psi was total. I don't suppose it. And another thing that we can recover from the discrete case is still true in the continuous case is that if C is densely defined, then the synthesis operator is extended by the adjoint of the analysis operator. Of course, if the domain of D is not dense, in general, it does not make sense even thinking of this the adjoint of D, and so does not make sense asking if the quality C is equal C equal to the adjoint of D is true. I proved that if A is a closable densely defined operator, then the domain of the adjoint of A is contained in the domain of C, and so it is densely defined, and B is closable. Another result is that if we have a sigma finite measure space, and we have a closed densely defined operator and a family of vectors in H, is equivalent saying that psi is a continuous weak K-frame for H, and saying that for every F in the domain of A star, of the adjoint of A, the map here is a measurable function on X, and there exists a closed densely defined extension R of the adjoint of C, which such that A can be decomposed as the product of R times M with M, a bounded operator on H to L2 of X. Then me and Rosario Corso extended the notion of atomic system for a bounded operator to unbounded operators. We defined it as as you can see here. We took a densely defined operator on H, and then we took a family in H if it is such that for every F in the domain of the adjoint of A, this is a measurable function on X, and these two conditions holds true, then psi is a continuous weak atomic system for A. I proved a theorem of existence if we have a sigma finite and sigma additive positive measure space with a covering made up of countable countably many measurable disjoint sets x sub n with a positive measure, and if we have a separable Hilbert space and A is a densely defined operator on H, then there exists a continuous weak atomic system for A. Then I proved, me and Rosario Corso proved in the discrete case, I proved it also in the continuous case, the characterization theorem equivalent to that one proved by Gabruta for a bounded operator, and we proved that if we have a closable densely defined operator and X is a sigma finite measure space, then is equivalent saying that psi is a continuous weak atomic system for A, or psi is a continuous weak A-frame, or psi is such that there exists continuous weak A dual phi, which is a Bessel family, for which this condition holds true for every f in the domain of their joint. And the last thing I want to say that if A is a densely defined operator and psi is a continuous weak A-frame, by the previous theorem we can give this reconstruction formula of the range of A, of course in weak sense, and this is why we chose the term weak for our definitions. And surprisingly, even though A can't be strongly decomposed, if we have a continuous weak atomic system for A, and a densely defined operator on H, and a Bessel continuous weak A dual of psi, then we can strongly decompose the adjoint of A. Thank you for your attention.
Thank you very much, Georgia. Are there any questions here? Professor Pavliković?
Yes. I would like to ask you have also questions.
I will read.
Some questions on the chat.
Okay, I will read it later. Maybe you can pose your.
I'm sorry.
There is a comment from Professor Fightinger.
I can't.
Just to have a good feeling, how you connect, or is it possible to connect, let me say, some basis, classical orthonormal basis with continuous frame somehow? Is it possible? I don't see, I was thinking how it should look like Cx, when x is, for example, real number. So what are examples?
I'm sorry, I can't hear you very well.
Okay, maybe I'm fine. So I just ask, can you give us some example of continuous frame? I mean, in relations maybe to some basis, orthonormal basis. Is there any kind of connection, or how we can imagine such kind of frames? Continuous Bessel sequence for atomic decomposition.
I'm not sure we have understood very well your speaking. I don't.
We have some helpers here. The little one.
I'm sorry, Professor. You asked me if there are there is any relationship between the orthonormal basis and continuous weak frames.
Bessel atoms, or how we call it. Bessel sequence. You work with Bessel sequences. That's I mean, this is C of X, C indexed by X. How it looks like, Cx. It's not much of Cx,
Professor asked, what does it mean, psi x?
How it looks
How it looks like.
Psi x is may I share again
yes.
my.
Just a moment, we will give you privileges. Share.
Just a second, because the chat is going crazy.
Just a sec, please.
Okay, you can.
Okay, now you can share the screen.
Okay. C'è un problema. I'm sorry. A disaster. Go.
Just say I put some information into the chat.
Yes.
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 Yes. You have a comment from Professor Feichtinger.
Yes.
So, yeah, it's.
To Stefan. For example, Reynolds system.
Wavelets.
X in Rx plus B. That is comment of Hans. Professor Hans. Of TF shifts or of Gaussian with X in yes, on R.
Okay,
Yes, but
thank you.
it is just okay. I read the chat. Yes, of course, everybody is right. Maybe you want to just to say to know that what is that function.
Yes.
Okay, it is just a function that associates to every element of a space of measure, as a measure space of a measure space. For every f in H, can you see my
Yes.
f belongs to. For every f in the Hilbert space H, we have a okay. I rewind. We have a family of vectors in H, for which for every f in H, this function is a measurable function on X. Okay, so you can think about a family psi whose elements are psi sub x with x in this in the measure space, varying in this measure space, such that this condition holds true. Okay.
Okay, thank you. There are also some other questions in chat. I don't know whether I should read. For instance, maybe we have time for one of them also. A question from Srđan Lazendić. You can see it in the chat. The atomic sequences for the classical frames came way before 2012. They are just called dictionaries in the discrete case. What is the difference between those atomic sequences and the ones introduced by Kuhn in frames generalized by nonlinear atomic functions? Do you have any concrete examples of those decomposition in practice? I mean, I read it because of the others, but you can see it, Georgia, in the chat from Srđan Lazendić.
Okay, I can see the chat now.
If it's not very convenient to you to answer that question now, we can proceed and you can answer later in the chat. Maybe it's better. Directly, yes, not to us, directly to Srđan. Because
yes, I could answer the question or privately or in another moment.
Okay.
Yes,
okay.
you want you can go ahead.
Okay, okay. Thank you very much for now, and thank you very much for your talk, and we will proceed. Thanks again. And we will now continue with our next speaker. This is Georgi Vučković. He is here in Novi Sad, and I hope that you see, do you see the screen? He will talk about certain convolution within ultra-distribution spaces, and so please, Georgi.
Okay, thank you very much. So I will talk about the recent work, so convolution with this type of kernel. So it's talking about convolution. It's nice because it's one of the most important operation mathematical analysis, but on the other hand, it is okay. Okay. So let's check this. Okay, so it's about this convolution. Almost always not so pleasant to talk about convolution because you have a lot of obstacles in your way. Fortunately, we were able to solve this problem, and I will present results. Let me first give you, let's say, outline, sketch outline of the talk. So first motivation, why, and then preliminaries, how. What are we talking about, and then go straight to the point. So we have some Q. Oh, this is not so pleasant. So we have some Q's greater or equal to 1, and we have S, and we have certain type of Gelfand-Shibboleth ultradistribution, and then we wanted to examine conditions for the existence of convolution of this type. So we want to convolve S with this kernel, and also we provide this necessary and sufficient condition. However, when Q is equal to 1, they are turned out to be the same. So both sufficient and necessary, and therefore we were able to characterize those distributions that are convolvable. It is based on the joint work with Professor Vučković and Professor Prangoski. As a matter of fact, it's a topic of the article we submitted recently. So let me give you a brief motivation. So of course, when we talk about linear amalgam spaces, and with this super exponential rate that comes along, this kernel is of particular interest. So where Q is greater or equal to 1. And then let's say we have a really good framework to work, because the convolution of Gelfand-Shibboleth type ultradistribution is really good done in this article, Vučković, Prangoski, and Hilbert. And so we tried to work out in this framework. However, let me give you some historical remarks. So the problem of distribution, how can we convolve distribution with the Gaussian? It was studied by Wagner, and it is, let's say, this kind of condition is given via growth behavior of those distributions. For ultra-distribution counterpart, it is solved by Professor Vučković and Professor Prangoski, because they examined variable and anti-weak calculus, because especially the connection between variable and anti-weak, the calculus is via convolution with the Gaussian. And therefore they were able to give a wide class of distribution, ultra-distribution that are convolvable with the Gaussian. And then there's a thing that comes handy, because this guy that is, of course, involved in the convolution, that can be split into a product of two parts. They can be easily controlled, these two, which is really good. However, when Q is not 2, then we don't have that kind of good behavior, and that we cannot apply the same ideas. Plus, of course, we lack the functions of compact support, and then there's also the problem we have. So we need first to give a good, really good bounds as sharp as possible on the derivative of kernels of this type. For the Bernoulli ultradistributions, if you work with those spaces, it is not so nasty. These are not so nasty for the convolution, and then the most of the results can be easily, let's say, transferred to the spaces of that type. So let me go to the preliminaries. And preliminaries, whenever we are talking about ultra-distributional settings, then we start with the sequence. This sequence, and with this one, okay, a lot of conditions that starts with M. For us, they are the conditions that we can do. We can see all of these. Each one of these conditions tells us about the classes of function, but you can think of this as some kind of constraint we need to put on the sequence in order to, let's say, bound the nastiness of the spaces of the functions. And if you're not familiar with this kind of sequence, then you should think about as a factorial raised to some power greater than 1, in order to, let's say, to have some kind of idea what are we talking about. And then let's see about the space of Gelfand-Shibboleth type. Okay, this is Q hidden somewhere above. So for every H greater than 0, we have the Banach space of all functions that are really rapidly decreasing. So look at this. So we take the derivative, and then multiply with this super exponential weight. And then this should be bounded by the order of derivative in this manner for the fixed H. And then we take inductive limit, which is basically, if you're not familiar with the topology, then you can think of this as a union in the set theoretical meaning. So we demand this to be true for some H. And then we take the strong dual. Oh, that's okay. Strong dual in the settings of locally conic spaces. And then we call the space of Gelfand-Shibboleth ultra-distributions. However, we need a second type of the spaces. These are these DL infinity spaces. It is the spaces, these are the spaces to hold the, let's say, smooth function for which the derivative is simply bounded and nothing more. And then we take union in the, as a set. In this is DL infinity space. And then the party comes along because we need a lot more, unfortunately. So we take, well, this space is really big, and it comprises all of these spaces of Gelfand-Shibboleth type. So we take the closure of this this space into this space, and then take its strong dual, which is actually not the most pleasant construction you will see. However, it does not depend on the Q. It does not depend on this Q, which is actually good for us, for our problem. And then the last thing actually to mention is this D prime L1 is really important for in terms of convolution. So this D prime L1 is, as a matter of fact, it is strong dual of this DL infinity, where the topology is slightly weaker than the original one. This is just something to have in mind. And then we need to we need to define a convolution because it's not so straightforward. So for the convolution, for two ultradistribution, so for two generalized functions of this type, then it exists if this nested thing belongs to D prime L1. However, for all the test functions that is rapidly decreasing in this way, where this is just simply, this is standard thing, and then we define it, we define this, let's say, function in a really broad sense applied to 1, where 1 is actually 1, the constant function, in this space. Okay, and then we just go a little bit to the details. So this is general theory of convolution. Then we can pick one of these equivalent conditions for the convolution. Well, we adopt this second one. It's interesting, and so this is just so ultradistribution admits convolution if this thing. So S multiply with this is the standard convolution of two functions. Then S multiply with function. We demand this to be in this D prime L1, this nested space, for all the test functions. When we have that, when this is the case, actually then this is defined. We apply this thing to 1. Once again, 1 is 1 as a constant function. Okay, so and then we start with some sufficient condition for the convolution with this type of kernel. For the sufficient condition, we need to be as precise as possible for derivatives of the kernel. So start with the lemma for derivatives, and then, of course, this lemma is we needed to examine derivative of this kind of function, but we need to be as sharp as possible. You can see these S, and these are the same. And then we have something like a polynomial, so finite number of terms here. So these we wanted to be sharp, and we did it. But the proof is just, unfortunately, by the funny formula that is following me all these years. And so for the consequence of this, we have this result. This is, if we allow ourselves a little liberty, then we can just pick this sufficient number of terms to be e to the power of this smaller term. However, I will just give you a brief flavor of the proof. I won't prove it because it's really a lot of gory details is involved. So this is the thing we use instead of, since we don't have the case where q equals to 2, then we need to use a lot of these kind of estimates of this type. And then, after a while, we were able to handle the whole proof. However, look at this. So we have the q1, and then the q, which is greater or equal to 1, and then s. If s multiplied this kernel and multiplied by something that is smaller with a smaller term for all k, then the convolution exists. So we have kernel and plus something a little bit more. However, once again, you can just see that we picked the case where q1 equals to 0, equals to infinity. Then we can simply, this is exactly the spaces of the completely supported differentiable function. And then if we take q1 equals to infinity and q equals to 2, then we just recover the results obtained by Professor Prangoski for the convolution of the Gaussian. So this is regarding conditions. So when the convolution, what needs to be done, fulfilled if we want for convolution to exist, and then we do the other way around. So these are necessary conditions. So these calculations are different. So we take some g, which doesn't need even to be smooth, just to be rapidly decreasing. You can see this rapidly decreasing, so that doesn't even need to have a derivative. And then we examined convolution, which is okay. It is not so hard to handle. However, this was really hard and really painful to get. 1 over convolution, because then we don't have a test function, and these guys are really nasty, and then we were able to perform this kind of calculation. Once again, we don't need for G to be smooth. And then look at this. So what happens for this? Okay, this. So we have once again this measurable function that is rapidly decreasing, but it's not 0. Okay, so not 0. We have estimates from above, both from above and below. Here, for the first time, we have for MP this sequence for which we didn't have a constraint here needs to be above p factorial. So, as a matter of fact, p factorial 2 to the minus 1 over q. And then if S satisfies, so S multiplied by this convolution, actually we will see. So if the convolution exists on the other hand, then this S multiplied by kernel of this type for every S prime less than S, then this is in the D prime L1. For the Q equals to 1, this holds for S prime equals to S, no problem at all. So just let me give you, in some sense, to translate this. So we have the Q1 and Q and S. So if convolution exists, then the 6 is just, no turning back. So the 6 was, how can I turn back? Okay, sorry. So this holds, this thing holds for all S prime equals to S. However, if we allow ourselves also a little liberty, then we can play a little with these indices. Then we were able to do this a little better. Then this belongs to D prime L1, so E, and then something slightly smaller. However, also again, as a consequence, what happens if the convolution exists? If Q1 is greater than 1, this holds. And once again, so this lemma, if the convolution exists, then also convolution exists for every S prime this is less than S, wherever this is not 0. And thank you for your attention.
Thank you. Thank you. Are there any questions? Do we have questions? Hello, everyone. We are back. So we are ready to continue to resume the conference. So our next speaker, Philip Tomić, the title of his talk, Boundary Values and Wavefront Sets. So please.
Thank you very much. So today, actually, I'm going to talk about boundary value representations of ultradistributions, a certain type of ultradistributions. Of course, in standard theory, it is well known that ultradistributions can be represented as boundary values of analytic functions. So actually, what is the main problem? It is to determine under which condition analytic function observed in a certain conical domain with respect to imaginary variable is a well-defined ultradistribution as epsilon tends to 0 in gamma. So this is this here is the classical result of Hermander, which says the following: if f is an analytic function and satisfies this type of estimates, again if epsilon is in gamma, then this here actually denotes what happens when we send epsilon to 0. So we get actually a well-defined Schwarz distribution. So this is, of course, the singular in the 0, but nevertheless we end up in this distributional space. So if we have this, I would say, polynomial, the decay of the polynomial type, then we are in the classical distribution theory. To be more precise, I will go to the alpha distributions, and this is just some technical things that we have. So actually the derivatives of such functions are controlled by these sequences here, and then we have a lot of technical conditions on these sequences that have to be satisfied. So we have this M1, this is our logarithmic convexity condition. We have M2, which is actually quite important because it gives ultra-differentiability, and we have this M3 prime, which means that actually in our analysis we can use completely supported functions. And then we have this condition M1 star, which is stronger than M1, that also has to be satisfied. And of course, there is an example of sequence. This is a Shearlet sequence, which satisfies all of this condition, and this is not actually hard to check. And we, of course, define the corresponding classes of functions, as you can see. So derivatives of the functions, they are smooth, but their derivatives are controlled by these type of sequences. And we have this, of course, with projected and inductive limits, which if we somehow, if we are not interested in topology, but in these settings we usually are, if we just look, observe these spaces as set of functions, then we, here if we take projective limit, then it is intersection. Here we take inductive limit, that it is union. So in that sense. And this is just the space of smooth, locally smooth functions in the sense of MP, and this is its subspace of compactly supported functions. And we have the duals denoted with this prime here. So there is one more notion that we need, that is the notion of associated functions. So each such sequence which actually satisfies these conditions on the previous slide, we can associate a function in this of this form, and we have actually one more function. This is the T star, which is actually obtained if we if we have NP over P factorial. So this is actually. So what is? How can we estimate these functions if we have Shearlet sequence again? Then this is just actually k to the power of 1 over t. And here we have this movement t minus 1 if we have this star. So this is well known from the Shearlet sequences. And this is actually the boundary value theorem, which is done by many authors. I wrote here Komatsu, and of course Professor Vučković have the book together with Professor Kaminska and Carmichael with a lot of versions of this type of theorem. what is the main idea here? So again, we have the analytic functions. Again, this imaginary part is in the code. And if it satisfies this type of estimate, where we have this T star here, again, it is singular at 0. Then when we let epsilon tends to 0, we end up in this D prime. And so we end up in the corresponding ultra-distribution space. So what we done actually, and here these actually the main thing is exactly the properties of these sequences. So all the properties M1 star to M3 prime have to be fulfilled in order to prove this type of result. But what we did actually, what is actually the topic also of my PhD thesis, we introduced the spaces in the following way. So we have very particular sequences here which actually control the derivatives of phi. And again, following the ideas of Komatsu, we take define the corresponding classes, similarly as in the previous slides. But what is actually the main observation? These classes are, of course, in C-infinity. This is said locally, they are locally smooth, but they also contain the union of Gevrey classes. So this is just topologically notation, topological notation. But when we take union, they are, so we are somehow between the Gevrey and the C-infinity. And of course, if we take the duals, then we are between standard Schlags distributions and let's say ultra distributions of Gevrey type. But what was the main obstacle when it comes to boundary values? Well, it's actually these properties which are not fulfilled. This property M2 star here, which is actually somehow generalization of, in our settings, of regular M2, is actually how to say, it is the most important property of the sequences, and it is not fulfilled in our settings, but which improve this type of estimates, where we have these movements with respect to parameter tau. And this is always the case, even if, of course, in the constructions, I will not go into any constructions here, but even if we define these sequences, which are also important in our analysis, again, if we want to estimate them, we have some sort of, and this is always the case here. So, as you can see here, when sigma is equal to 1, then we have the Gevrey case, when this tau is greater than 1, and then we have just the regular Komatsu conditions. But if sigma is strictly greater than 1, then of course we have this, let's say, generalization of standard conditions. But although M2 is not satisfied, we can define partial differential operators of infinite order and prove that our classes, well, they're not closed, but again, actually, if we take union of our classes with respect to parameter tau, then it is closed. So we can actually construct a class of functions between Gevrey and C-infinity, which have the ultra-differential property. And this is the notion of associated function in our setting. It's similar to the standard notion, except for this here factor h to the p to the sigma. And it's important because, of course, of the new properties of this sequence NP. So we have to add this have to add this H here. And then what we can actually, so if we take star, what we can actually see that they are equivalent in some sense. So we can actually estimate this star between two these. So if H is strictly greater, then large H is strictly greater than small h, then we have this type of estimate. So actually, in our analysis, the use of T star is unnecessary. So we can do it all with this just T here. And do we have some, because we have very particular sequence, can we get very particular estimates for our functions? Well, yes. And here are the estimates. So what we have here is actually a sort of moderating behavior. So we have this k to some, this is actually, this in the exponent is slowly varying function. So we have Lk or Lk, product of Lks. Somehow this holds, and of course this is just variant. So if we have here these constants, we don't mind about this C2 constant because this behaves like this. So actually this here is the most important part. So this is actually the boundary value theorem. In our setting, it is not what is the difference actually? Well, the difference is, of course, we use our functions, not star. It is enough just to use T here. And of course, again, these movements with respect to the parameter tau are always present in our settings. But what is interesting here, what happens if we now take the intersections and the unions with respect to this tau? And to present that, I will just briefly go to the notion of wave sets. Okay, this is just the standard definition of the wavefront set. So we always define it on the complement side. So the point is not in wavefront set if there exists a conical neighborhood of psi 0 and a compact neighborhood of x0 and the compactly supported functions such that this has to be solved where this T is again our associated function. And what we can immediately prove is that these wavefront sets are between standard wavefront set and the intersection of all Gelee wavefront sets, or not, of course, the Schwarz distribution. But what if we take now, if we take intersections and unions in the test case, P with respect to tau, then we can, of course, do the same thing with wavefront sets and define it for this type of distribution. So we define the dual spaces of these and then take the corresponding intersections and unions of wavefront sets. And then we can actually prove the following. Well, this is not exactly the correlate, but it's more like a theorem because no, sorry, this is correlate. This is actually the characterization of these intersections and unions of wavefront sets. So here we have very particular decay of this Fourier transform. So we do the localization, and then we take the Fourier transform, and it decays in the following way. Again, we have these estimates on our associated function. And when we have this type of characterization, we can prove actually this should be actually corollary. Okay. But what we can do here is here we have intersection and unions of our dual spaces, and we can actually say that this F here has again very particular behavior, let's say logarithmic behavior, singular again in the zero. And then we can say when we let epsilon tends to zero, we end up in this space. So this is the boundary value result for these intersections and unions. And moreover, we can prove that wavefront sets, corresponding wavefront sets are somehow in a dual form. This is just a notion of dual form with respect to this number. So, to conclude, I will just give a list of some references related to this topic. And thank you.
Thank you. So here we have questions. So we have a question: how do you compare your weight sequences with the group Reiner and Schmidt via weight matrix systems? It seems to me that your generalization of the Shibboleth sequences might fit to that approach. Is it true? Уф, на някакво тежко време не добра. Nothing.
Okay, yes. I think that with that approach, I'm not sure, but I think that with that approach, they try to, again, they did not leave the standard settings. They simply wanted to, I think, study intersections and unions of Shibboleth spaces. But I think that even if you take this matrix of sequences, I don't think that you leave these standard settings, which we hear. So our sequences are much faster than Shibboleth sequences. And therefore, they do not satisfy the standard conditions. But if you take intersections and unions of in that matrix approach, I think that they only take intersection if you have the Shibboleth sequence to the, I don't know, p factorial to the t. They just take intersections and unions or just change the parameter t. But I don't think that they leave the standard settings.
Did you read another question? There is another question. So.
Da bi upadao u klasu funkcija Hansa Taylor, to ne upada u tu teoriju. Ne zadovoljava svoje alfabeta.
Maybe just repeat because of the others.
I'm not sure about the second question, but about the first question, I'm pretty sure.
I think that, again, I don't know, better condition is not satisfied in the approach of line tape. They have alpha, beta, gamma condition. Then one of them is also broken.
Okay, do we have questions here? No? Okay, so no other questions in chat? No. Okay, thank you very much. So we still have 3 more minutes. Should we start earlier? Is Francesca Bartolucci online?
Yes, I'm here. Can you hear me?
Yes, we can hear you.
Okay.
Great. So can we start? Ready?
I share the content.
Okay, just take it easy. So our next speaker is Francesca Bartolucci, and title of her talk is Continuity Properties of the Shearlet Transform and the Shearlet Synthesis Operator on the Lizorkin type spaces. And okay, you already shared the screen.
Can you see my screen?
Yes. Yes, we can see it. So please, you can start whenever you're ready.
Thank you very much. Thank you for the introduction, and thank you to the organizers to give me the possibility to present this joint work with Stevan Pilipovic and Nenad Teofanov, and that we have developed in the last year, starting with my staying in Novi Sad last January. And this work is about the development of a distributional framework for the Shearlet transform, which is an integral transform that is related to the Shearlet representation. Before recalling the definition of the Shearlet transform, I would like to recall some basic definitions in the theory of representations. So in order to motivate and to give the framework of our work. So I start, with the definition of square integrable representations. So we take a group G, which is locally compact and second countable, and we consider a unitary irreducible representation of the group G on the Hilbert space H. I recall briefly that the representation is a group homomorphism from G on the group of unitary operators on H into itself, and we say that the representation is irreducible if the only closed subspaces invariant under the action of the representations are the trivial ones, so all the space H and the null space. Every time we have a unitary representation, we can define the so-called Voice transform associated to a fixed function in the Hilbert space H, which is an operator from the Hilbert space H in the space of continuous and bounded functions on the group. So the Voice transform takes a function in the Hilbert space H and gives a function on the group, and a value at a point G and in the group is the scalar product of F with this element, which is obtained acting on with the unitary operator pi of G on the window psi. And if there exists a function psi in the Hilbert space such that the Voice transform takes values in L2 of G and is a non-trivial multiple of an isometry, then we say that the representation is square integrable, and we say that the function psi is an admissible function. In such a case, we can consider the adjoint operator of the Voice transform, which is called synthesis operator, and which is given by the following weak integral, in the sense that this element is the element in the Hilbert space whose scalar product with all the other elements in the Hilbert space is given by the following formula. So a classical issue in harmonic analysis is the question how to extend this Voice transform from Hilbert spaces to more general spaces, so spaces of distributions. And there are at least two classical approaches. The first one, for sure, the theory of distributions introduced by Schwarz in the early 50s, in which we consider a transpose mapping of the Voice transform, which is defined by the following relation here, which holds for every f in H and every phi in L2 of G. And here on the left, we have the dual pairing in L2 of G, and on the right, we have the dual pairing in the Hilbert space H. And in such a case, the transpose mapping is strictly related to the adjoint of the voice transform. Indeed, it is exactly equal to the adjoint up to take the conjugate of the window. Then we define a pair of locally convex topological vector spaces in order such that the transpose mapping is continuous between these two test function spaces, and such that the test function S embeds continuously and densely in H, which ensures us that H embeds in the topological dual of S. So if we have this continuity property, we can extend the voice transform from H on the topological dual S prime by duality, so as the transpose mapping of this operator between these two test function spaces. So classical examples of this approach are for sure the extension of the Fourier transform from L2 to temporal distributions, and other examples are the extension of the radon transform to distributions, and I refer to the work of Helgason, Hertel, and also to the more recent paper by Konstantinova, Filipovic, Saneva, and Vindas, in which they extended to distribution both the Richlet transform, and they also achieved new results for the radon transform. And I also want to refer to the extension of the wavelet transform to the distributions given by Olschneider in his book about wavelets. And these two works, so the work by Olschneider and the work by Konstantinova and collaborators, are the works that most inspired us for our paper. So the second approach to extend voice transforms from Hilbert spaces to generalized function spaces is the Corbett space theory introduced by Feitinger and Gröchenig at the end of '80s. And it applies whenever we have a square integrable representation pi of a group G on a Hilbert space H, and whenever we have a set of analyzing vectors not empty. So we define the set of analyzing vectors starting from a weight function on the group, and we say that psi is an analyzing vector if it is an element of the Hilbert space H such that the voice transform associated to psi and evaluated in psi is a function on L2 of G, and this is equivalent to require that psi is an admissible vector. And we also ask that this function is in this L1 weighted space. So if this set is not empty, we take one analyzing vector psi and we define as follow the space that plays the role of the test function space, and which is denoted by H1W, which is the set of elements in the Hilbert space such that the voice transform of F is a function on the group in this L1 weighted space. This space is proved to be a Banach space, is proved to be invariant under the action of the representation pi, and it is also possible to prove that it embeds continuously and densely in H, and this ensures that H embeds in the antidual of the test function space H1W. So these continuity properties allows to extend the inner product of the Hilbert space H as a sesquilinear map on the product of the antidual times the test function space H1W. And we can extend the voice transform as follows. So the voice transform of an element of the antidual T is a function on the group, which is defined as follows. So the evaluation in G is the action of the element of the antidual on this element, on this test function, which is obtained acting on the window psi with the unitary operator pi of G. And this is a good definition because psi, by definition, is in the test function space, and we have said that the test function space is invariant under the action of the representation. So in the Corbett space theory, the fact that we extend the voice transform is not the end of the Corbett theory, but is just the first step. Because once we have this extended voice transform, the so-called Corbett spaces are introduced, are defined, requiring decaying properties to the extended voice transform. And examples of Corbett spaces are, for example, the classical Bezos spaces, which are recovered starting from the affine group and the wavelet representation, or the modulation spaces starting from the reduced Heisenberg group and the Schrödinger representation. And this theory was already been applied also to the Shearlet case, so to the Shearlet transform, and new smoothness spaces, the so-called Shearlet-Corbett spaces, have been introduced. So in our work, we want to develop a distributional framework for the Shearlet transform using the first of the two approaches, so the approach given by Schwarz. So our work is motivated by the fact that studying at the same time the Shearlet transform, the wavelet transform, and the radon transform, we realized that while the radon and the wavelet transform have been widely, deeply studied and developed also in the distributional case, this was not true for the Shearlet transform. So the idea is to consider the Shearlet transform and its adjoint, the so-called Shearlet synthesis operator, and based on the duality approach given by Schwarz, we develop a distributional framework for the Shearlet transform. Since a Corbett theory already exists for the Shearlet transform, we have to look at the previous results and to prove the consistency of our definition of Shearlet transform of distributions with previous results. And finally, we proved that some central results in representation theory, for example, the existence of reproducing formulae for in the Hilbert space, these reconstruction formulae already hold also in the distributional case. So I briefly recall the definition of the Shearlet transform, which is the voice transform associated to the Shearlet group. The Shearlet group is the semi-direct product of R2 with the semi-direct product of R with R times, which is R minus the zero, endowed with the following group operation, where here this matrix is the so-called shearing matrix, and here we have an anisotropic dilation matrix. It is possible to prove that a left R measure on the Shearlet group is the following one, where here we have the Lebesgue measures on R2, R and R times respectively. And it is possible to prove that the standard Shearlet group acts on the Hilbert space L2 over 2 via the so-called Shearlet representation. The Shearlet representation takes a point in the Shearlet group and gives the following unitary operator, which acts on a function in L2, translating the function with a factor b and performing these two transformations on the function. So this transformation is called the shearing, and then we have an anisotropic dilation. So we have the Shearlet group, we have the Shearlet representation. We can define the Shearlet transform, which is the voice transform associated to the Shearlet group. So following the definition in the first slide, we can define the Shearlet transform as follows. So is an operator from L2 over 2 into the functions continuous and bounded on the Shearlet group. And the Shearlet transform of a function f in L2 is a function on the group with whose value at a point in the Shearlet group BSA is the scalar product of f with the window psi, which is transformed as we saw before. So on which we apply this unitary operator. It is well known that if the window psi is such that the following admissible condition is satisfied, where here f is the Fourier transform in L2 over 2, then the Shearlet transform is a non-trivial multiple of an isometry from L2 over 2 into the space of square integrable functions on the Shearlet group. So the Shearlet representation is square integrable, and in such a special case, the admissible functions are also called admissible Shearlets. Then we can consider its adjoint operator that we call Shearlet synthesis operator, and which is given by the following weak integral. Then an important issue in the theory of representation in general, and here I present the special case of the Shearlet transform. We have, so every time that we have a square integrable representation, we have reconstruction formula for the Hilbert space. So in this case, for every f in L2 over 2, we have the following reconstruction formula, which states that we can recover f starting from the Shearlet transform of f. This reconstruction formula is in general is to be read in the weak sense, but if we impose condition of smoothness or decaying on the window and we restrict the signals that we want to recover, this formula can also hold pointwisely. And we observe that this reconstruction formula can be written in terms of the Shearlet transform and its adjoint. And in particular, this formula states that the Shearlet transform is injective and the adjoint of the Shearlet transform is surjective. So the Shearlet transform was introduced in this paper by Gitta Coutinho and Demetrio Labate, and has gained more and more attention in the harmonic analysis community and also in the signal analysis community for its capability to solve the wavefront set of signals, as it was proved both in these two works. And this is due to the fact that wavelets they have translation and dilations, and as you saw in previous slides, in Shearlets we have also anisotropic dilation, but also this transformation. And this transformation inside, so in the group structure of the Shearlet transform, allows the Shearlet transform to give information about the singularity set of signals. And this is the most important feature of the Shearlet transform. Then now that I have recalled the Shearlet transform, I want to state the main results. So as I already mentioned, we would like to develop a distributional framework for the Shearlet transform following the Schwarz distributional theory. And so we need to introduce the test function spaces that will be involved in the continuity theorems. So we denote by S over 2 the Schwarz space, and by S prime its topological dual. And we denote by S0 the space of Lizorkin test functions, which is the set of Schwarz functions with all vanishing moments. This is a closed subspace of the Schwarz space, and it inherits from the Schwarz space the topology of closed subspace. And its topological dual is the so-called Lizorkin distribution space, and is proved to be canonically isomorphic to the space of temperate distributions over the set of polynomials. And this space of distribution has already been shown to be a natural domain for the Radon transform, the wavelet transform, and also for the Ridgelet transform. And we will see that we can extend the Shearlet transform exactly to this space of distributions. And this fact is not very surprising for us for two reasons. The first one is that, as we showed in this paper here, the Radon, the wavelet, and the Shearlet transforms are strictly related. And the second fact is that condition on vanishing moments is, it was shown to be essential when we want to characterize regularity and smoothness of signal in terms of the Shearlet transform. So then we introduce the other test function space on the group. So is a sort of Schwarz space on the Shearlet group, and is a space of functions, C infinity function, such that this family of semi-norm is finite. And the role of these semi-norms is to control the decaying properties of these functions with all their derivatives at infinity with respect to the parameter B and S, and the decaying at infinity and also in zero with respect to the scale parameter. And we denote by S prime its topological dual. And as it happens for the Schwarz space, if we have a function which is a slowly growing function, we can identify this function as an element of the dual S prime. So now,
just please 1 more minute or two, please.
Okay.
Okay.
Perfect.
Okay.
Yeah.
Thank you very much.
So the main theorem is the following one, which states that this pair of test function spaces is such that the Shearlet transform and its adjoint are continuous. And these continuity properties allows us to extend the Shearlet transform and its adjoint by duality. So we can define the Shearlet transform of any Lizorkin distribution as the transpose mapping of this operator, which is continuous. So the continuity ensures that is a good definition. And we can define the Shearlet synthesis operator of any element in this dual space as the transpose mapping of the Shearlet transform. And the continuity property of the Shearlet transform ensures that this is a good definition. And once we have the definitions of generalized Shearlet transform and generalized synthesis operator, it is not difficult to show that the reconstruction formula that we had in the Hilbert space holds true also for any Lizorkin distribution. And finally, the other main theorem is the following, which states that our definition is consistent with the one given by Dahlke and collaborators in the context of Corbett spaces, because it states that the Shearlet transform of any Lizorkin distribution is a regular distribution, which is identified by the following function, which is a function on the group smooth and most polynomial growth. And the evaluation at the point in the group is the evaluation of F on the window on which this unitary operator acts. And finally, from this theorem, we can we have this desingularization result in the sense that we can write the action of any Lizorkin distribution as an absolutely convergent integral, where here this is the function that identifies the Shearlet transform of the Lizorkin distribution F. So this is the last result, and thank you very much.
Thank you. Thank you very much. Do we have any questions? Do we have questions in chat? Not so far? No? Okay. So if not, thank you again. Thanks.
Thank you very much.
And the last speaker for this session is Svetlana Mincheva-Kaminska. Is Svetlana here online?
Yes.
Svetlana, do you hear us?
Hearing you.
You should unmute the microphone.
She's here.
Hello, Svetlana.
I'm hearing you. What about you? Did you hear me?
Yes, yes, we hear you well. Welcome.
Okay, welcome.
So you're our next speaker. The title of your talk, Fractional Calculus via Convolution for Distributions of Several Variables.
Yes,
So
I'll
please.
try to my screen.
Yes, you can share the screen.
Yes, I try, but it's okay now?
We will wait. Yes, it takes some time.
It's in?
We don't see anything at the
I'll try
moment.
again.
Oh, wait a second.
Wait a second, yeah.
Could you try again?
Okay.
Okay, we can see. Let you start, yes.
Okay, now we can see it.
Okay. Thank you very much for possibility to take part in this conference dedicated to members of faculty. My speech is on the border of the theory of fractional derivatives and the convolutions, and I'll only check the first 2 points of this presentation because the definition of fractional derivatives of functions are very well known for the sum of participants, and also the definition of distributions and the convolution of distributions are very well known for the other participants of our conference. At the beginning, let me only to show some very well-known definition of Riemann-Liouville fractional integrals, and for us is important to show these formulas for partial Riemann-Liouville fractional integrals and respectively so-called mixed Riemann-Liouville fractional integrals in the case when we use the integration over the sum of all n variables of the converted functions. Here on this slide, we present the very important for our so-called semigroup properties of this fractional integral of non-negative orders for functions. Here is shown this semigroup property for the so-called right side integrals, and the second is the formula for the semigroup properties of the right-hand side fractional integrals for the case when the order of integration is non-negative. And here we have this formula 4 of the partial Riemann-Liouville fractional derivative of function of arbitrary complex order in case when the real part of this complex numbers in C have a non-negative real part. And in this formula, capital lambda K is such a real number, which is the real part of alpha K, respectively, plus 1. Here is this mixed derivative, and for our aims, the most important is this example 2. This is example of derivative of order alpha of arbitrary powered function x to the power beta, where beta is greater than -1. And we have such form of this derivative of order alpha on the so-called positive coin. We consider this power function on the space Rn plus, where all components are non-negative. And now I will not repeat all known definition of test functions or the respective spaces of distributions and temperate distributions. For us, it's essential that the space of locally integrable functions may be considered like distributions. We consider also the measure Dirac function together with derivatives of this delta measure, which will be shown in the next slides. And here we have representation of delta Dirac function as a distribution. There is the usual well-known definition of derivatives of distribution. You see it in the case of a multidimensional Heaviside function, which derivative of order 1 is just a delta Dirac measure. And now here we present only in several slides the definitions of Schwarz and Chevalier for convolution of distributions, and they are very well known for some of participants. For us, it's essential that the conditions S and C in these definitions of Schwarz and Chevalier are equivalent. Moreover, when one of these conditions is satisfied, both this convolution exists and are equal. Here we have the condition written in the terms of supports of distributions. If sigma and theta are the supports respectively of distributions S and T, these three conditions for these supports are conditions for compatibility of the sets of the supports of this distribution, and when these sets are compatible, then considered distributions are convolvable, of course. Now I'll only show some very simple but useful properties of convolution of distributions connected with his derivatives. We know that the delta Dirac measure is an unit element of convolution in the space of distributions, and also the derivative of order of national order M of distributions may be represented as a convolution of the derivative of order m of delta Dirac measure with the convolution T. Here is presented also the of convolution. On this slide, I also repeat that the power functions x to the power lambda and x to the power m with positive integers lambda and m may be the convolution of these power functions may be considered like distributions, like a distribution defined by formula 13. And here we'll present the idea of Gelfand and Shearlet to treatment the in locally integrable functions x to the power lambda, where we consider them defined by these formulas. And the interesting idea of Gelfand and Shearlet is to treat these functions like functions of this complex argument, like respective temperature distribution for the arbitrary complex number with real parts greater than -1. This formula here allows us to have such a kind of treatment of this power function. And what is essential for us? That the right-hand side of this formula 14 is considered as an analytic function of variable lambda, which can be analytically continued for every national m to the domain of a real part of lambda greater than -m-1 by this condition. And this continuation is presented in formula 15, where phi is an arbitrary test function. It is for us that this formula, considered like a function of lambda, is an analytic function which have meromorphic functions, which has a simple pose in points lambda equal to -k, and its residues at these points are equal just to the derivative of delta measure of order k-1. On the other hand, when a real part of lambda is greater than 1, we have formulas for the derivatives of these power functions, like distributions, and we see that these derivatives are just the usual derivatives of power functions. Now, we may consider also the gamma function defined by this formula. Also, we may consider it like as a value of the some functional considered like a temperate distribution of the test function e. E is the e to the power minus x when x is non-negative. As above, we also may use analytical continuation of this function to the domain real part of lambda is greater than -1 minus m-1 by this condition, using the analogous formula. And in this case, also, this gamma function, considered like a functional, is an analytic function in the domain when real part of lambda is greater than -m-1, and also has a simple pose in these points, these negative. And now the main idea of Gelfand-Schirruf is to consider this quotient like an entire function, and on the other hand, like a distribution on the half line. Then it appears that the values of this distribution at these points, lambda equal to the minus k, are just the derivatives of delta Dirac measure of order k minus 1. Then show that these functions, functions considered like distributions, also have a following semi-group property. We show that this property is also true in multidimensional case when the respective function E is the respective product of these exponential functions, the respective value of functional also is considered like a multidimensional integral. And also the respective values of these quotient considered like distributions are just the respective partial derivatives of delta measure, delta in multidimensional case. And what is the main result of our consideration? We showed that the generalized function phi lambda have the following semi-group property for arbitrary vectors of multi-complex numbers. And we may define the fractional derivative of distributions T of order of arbitrary complex order lambda in case where lambda has a positive real part. Then these derivatives are defined by this formula of fractional integral and respectively the derivative of fractional order. In fact, these are derivatives of complex order. Then we show that these derivatives may be have the respective convolutional form, and this form is given in this the derivative of complex order lambda is just the convolution of this distribution with the generalized function phi minus lambda. Having in mind this semi-group property, we obtain that this representation has a very simple application in two cases. The first case is considers the Abel's integral equation in multidimensional case for distribution considered in positive cone. Here is the theorem which presents the solution of such Abel's integral equation. Let us consider this Abel's integral equation of type 29, where S and T are arbitrary. T is looked for distribution, and S is a given distributions with arbitrary vector of complex number lambda, which has a positive real part. Then the solution of this equation is given by formula 13. And here on the next slide, I present only a very simple example of such multidimensional Abel's integral equation in case when on the right-hand side there is a derivative of delta Dirac measure of order beta, where beta is an arbitrary complex vector which has real parts non-negative. And the solution, of course, has this convolution form. And using given on the beginnings example of convolution of two power function considered like a locally integrable function, we have a decision, we have a solution, excuse me, of this equation of this form. On the next slide, I show maybe a simple example of such kind of solution for these concrete vectors, beta and lambda. And let me at the end show only the possibility to find a solution of the respective Fractional differential equation analogous to the wave problem with the respective wave operator for given distributions T in the space R n plus 1 and two distributions in space R in positive coin, of Rn, we look for a suitable distribution as satisfying this equation 32 for arbitrarily complex vector with these positive real parts, such that the sum of these components of the vector are greater than these real parts. Sorry, these have to be the real parts are greater than 2. And then the differential equation 32 with a given lambda has a unique solution as of this form. This is, of course, the convolution form of the solution, where V0 and V1 are given by these formulas. They are the respective convolution of the so-called initial initial conditions with the respective generalized functions. And I thank you very much.
Thank you, Svetlana. Thank you. Are there any questions? Do we have questions in the chat?
Yes.
No, we have no questions. Actually, there are no questions for you, Svetlana. So thank you very much again. And thanks. Thanks to all speakers in today's afternoon session, and see you all tomorrow.
9 o'clock.
9 o'clock, yes, we start at 9 o'clock.
Thank you.
Thank you.
See you tomorrow.
Thank you for today.
Thank you. Bye-bye.
Bye. Thank you.